Everyone. Welcome to Monday night and another edition of The Physicist and the Philosopher. Hello, Claudia. How are you?
Hello, Wayne. I'm very well, thank you. And how are you?
I'm doing well, and she is the physicist. I am not. I don't want to be. But
philosopher.
I be the philosopher. So, you know what, Claudia, I think the best way to always approach any subject is probably with laughter and lightheartedness. Because, when you start really getting serious about it, you start getting stressed.
Yes.
And we all know what those tests are like. I had remember I had a trigonometry teacher that, what an ass.
Oh my.
But, and I liked math, but this guy just made it so hard. And, then I look at the other classes I took. For instance, I loved architectural drawing. That was fun.
Yeah.
Yeah, and it's still. So, how has your week been?
Okay. Bit of work, too cold still for me. I'm not used to this cold weather here, but
Well, yeah, and that's going to be, summer is coming, so they say.
Yeah. Yeah, I mean, I've had quite a few attacks from the trolls recently. They even threatened my family, my brother, and my son, and things like that.
I heard Scott video on that, and I don't understand closed minds. This is no different than the Spanish Inquisition. This is no different than the Salem witch trials. This is no different. I can go on with the same thing with the KKK, with the lynchings. This is what these individuals equate to, because when you try to suppress free thought, and when you try to suppress a thought because it doesn't agree with your ideology, your theology, then you are the persecutors. And I won't tolerate it. If I see them in this room here, they're out. Listen, what I appreciate most about you, Dr. Albers, because we're going to get into something here, folks. Our professor here is getting well known, but anyway, is the fact that, as you said last week, as we closed the show out, was the fact that what you find more important about your students was not so much that the fact that how they could express your homework assignment, but was the fact that the free thought that they put into solving the equation.
Yes.
And I'm sorry to hear that, because that represents a part of humanity that needs help. And I just want to say hello to everyone in the chat room. Thank you all, the moderators, Sue G, Brenda Fisher, Milky Way Weekly. Thank you all, and welcome everyone. So this is a place that we challenge such small-mindedness, that to threaten another person's life, who gives you that right?
Yeah, Wayne, in this world, truth is always attacked. Whenever someone moves against the mainstream, against the tide, comes up with new ideas, these ideas are always attacked. It's always been like this. Yes. It hasn't changed.
It has not.
If I was going with mainstream, then everything would be fine. But I've been attacked because I found something and I decided to research it and find out the truth about it. And I decided to tell the world about it. I decided to tell normal people. I think normal people are intelligent enough and to be able to understand physics.
I agree.
And it's not just because you are trained to be a physicist. Basically, all I ever wanted was to teach people how to access this understanding about the universe. And that's what I did with my students. I used to tell my students, look, I am training you to be physicists. And this is the way you think. And this training you go through is to train your minds to stop and break things up and look at one thing at a time, because our minds are limited. We cannot cope with the whole universe in one go. We want to understand the whole universe. This is what physics is about. But we can only cope with a little bit at a time. So and physics is about solving a problem. You ask a question like, why is light reflected? How is it reflected? Why is it reflected? You ask a question, and then you say, okay, what's involved in reflection? It's light. It's the angle of the light. It's the medium. Okay, so let's take it apart. We have light, we have a mirror, we have the medium. So that's three things. We can only actually look at two at a time in an experiment. So let's see what happens to light in a couple of different mediums first. Let's see what happens to light if we hit a mirror with it at different angles. But that's two experiments. You see, you have to separate it and look at each separately. And then you start to picture and put together and start to understand what happens with light and what it does. What is a mirror? What happens when it's reflected? And then you may go on to refraction, which is the bending of light. You see, when you're doing physics, you're answering a question, you're trying to solve a problem. But most of us are, in our minds, let's just get to the end of it. Okay, so we miss all the details in between. Whilst the physicist, that mind has to actually be trying to stop and open things up and look at the details inside and look at them one at a time. And this is one of the reasons why it works so well for me to write articles, because as I am writing, writing forces you to slow down your thinking process. And physics is about doing that. You have to slow it down and consider each thing involved. And so when you are writing, you have to turn it around a couple more times in your mind. And so you start to understand more of the details and the connections. So physics is both creative and logical at the same time, because there are always gaps in the understanding. And at those times, you have to make jumps, intellectual, creative jumps, and you have to come up with an idea about how this may be connected. Then you will go and test it out by thinking of it in another context. So it starts with observation. You start by observing something. You start observing the fact that you can see yourself in a mirror. And then you realize that you are here, but you see yourself there. What is happening? And then eventually, by thinking about it, you realize, oh, but the light that's reflected off me goes towards the mirror and it's reflected back, and my eye is picking it up. It takes a lot of thought to figure that out. It doesn't just come easily. This is what physics is about. It's about understanding what's happening in our environment. And when you start understanding what's happening in our environment, you start understanding, going deeper, saying, what is light? Why the space? What is this we are in? And then you have to start defining things. This is where mathematics comes from, because we have matter, we have light, we have energy. All of these interact. But first we had to discover that there is matter even. We had to come up with an explanation of what are these things that we are touching. And we started calling that matter. And then we started seeing that there are these things that happen, that matter can change from one form to another, and energy can change from one form to another. So you get electrical energy, you get mechanical, which is the movement of matter hitting other matter, causing transformations of energy. And we started tracking this thing called energy. And energy is a very abstract concept. It can only be seen actually because things change. If nothing changed, then we wouldn't be aware of energy at all. It's like accounting. We keep track of energy by accounting what's lost here, what's gained there, and then we see that things are changing in the universe through these processes.
Now, I see that as a philosopher
Mm-hmm.
is two ways. First of all, when I see the equation of the universe, I can only see it through the limited experience that I as an observer is.
Mm-hmm.
And I've come down to this equation, Dr. Albers, is this. I wasn't aware of my birth and I didn't fear it. So I have no need to fear death. What I have in between is the opportunity to observe the universe.
Mm-hmm.
And that is what I take with me.
Okay.
And
that's good.
You see how and that's how I see it, because there's a symmetry there.
Yes.
And we see math, at least I do. I see math as the universe, the language of the universe.
Mm-hmm.
It helps define a construct that's very difficult otherwise to explain.
Mm-hmm.
It really is. The second aspect of what you were saying in explaining how physics begins to look at a problem, and then the goal is to solve the problem.
Mm-hmm.
And that there is a discipline by which you have to follow in order to either derive or to come to a conclusion that can be validated, right?
Mm-hmm. That's right.
So
go
ahead.
Yeah. The thing is, everything starts with a question.
Yes.
Actually, everything starts with an observation. You observe something happening and you ask yourself, what did I observe? What causes that to happen? And then you follow from there. You track. Every time one question is answered, it opens up a whole lot of new ones. Because you say, what is that? What did I see? So you start tracking that. Then you start thinking, okay, but what causes that? What led to that? And so on and so forth. So it's about, starts with an observation, you ask a question, and then you have a problem to solve because there are always many options.
Yes.
So sometimes it's trial and error. Let's go with these two options that may be connected. You test the connections, or you start using things that you already know to try and answer this particular question. Now, the process of problem solving is always a logical step-by-step process that's supposed to lead you to an answer. But you have to always start from the right premise. If you start from the wrong premises, your answer will be meaningless. That's the problem.
That's good.
So this is where physics is failing nowadays.
Interesting. Now let's talk about that.
Yeah. So there have been a whole lot of theories that have come forward and have been accepted by mainstream physics. because they're comfortable with it. But when observations come that say this theory is wrong, they throw out the observation. They refuse to move from the theories that have been shown over and over and over again through observation to be wrong. And that is the Big Bang Theory, the standard model of particle physics. Most of the standard models are wrong, and most particle physicists know it's wrong, but they refuse to move from it, and it's become politicized, basically. In other words, if you don't go along with it, you lose your career.
Yeah, the fatal coup de grace.
Your papers are not published. You may lose your teaching positions. It has happened. It happens. Or you don't get promoted. You don't get the chairs, research chairs. You don't get time on the telescopes. You don't get invited to CERN. You kept out of the mainstream. Your papers, you think your papers are getting a fair referee view, but they're not. The referees always come back with something wrong with your paper. You fix that. It's sent to the referee again. They find something else that's wrong, so they delay. They don't get published.
It's a form of censorship is what we're talking about here.
Physics is horribly censored. And the peer review system is a gatekeeper that keeps the new theories out of mainstream. So,
well, let me just ask you, you could look at this from a conspiracy point of view.
Mm-hmm.
So what you're saying is there seems to be a cartel of somebody or some panel or some groups of somebodies where basically the ability for our species to come up with original thought is somehow or another frowned upon.
It is, especially if you go in a direction that they don't want you to go in. I think in about the beginning of the 20th century, mainstream physicists or whatever's behind it, this deep state, Illuminati, whatever, was decided we cannot let mainstream physics go in this direction. We have to block it.
What are they afraid of?
And this is where it started. So they're controlling whatever the universities, whatever research is allowed. The money only goes into research areas that are allowed, that does not bring people to the correct understanding of what the universe is like.
What are they afraid of, Claudia? There's something that they're afraid of here.
They're afraid of their power being eroded. And their power is based on the population on this planet being ignorant of certain things.
Do we want to define those certain things?
First, certain things is, I believe they don't want us to understand what the universe really is like, because then we would understand the technology that is possible and that they obviously have and we don't have. For example, free energy should be possible.
Sure. I think it should have already been here. I think that's why they murdered Tesla.
Exactly. Yeah. Anti-gravity is possible. The way the sun works, it's electrical. It brings you understanding of how the universe really works. They don't want people to understand what is happening in the solar system. Don't forget the objects that we've been talking about have been here for a long time. They don't want people to understand what's happening to the Earth.
Keep talking, because I'm going to show everyone here Dr. Albers today, ladies and gentlemen. I think in a lot of ways, Claudia, I'm so proud of you, and it's just an honor to call you a friend. And colleague. And so I'm going to pull up this for everybody to see, and I'll let you just keep on talking. But everyone, just to let you know, Claudia, you were actually interviewed today by the UK Express, right?
Well, I wasn't actually interviewed. I didn't know they were making this article about me.
Oh, you did not.
All of it was the truth, but I think it did highlight some of what is going on. I had a live stream with Scott earlier in which we went through it. And I talked about what actually happened. It talks about what the University of the Witwatersrand, where I worked, what they had to say about me, what they did. We went into a little bit of what the trolls did, how they threatened the university, how I had to leave because of what was going on, even though I never wanted to go public or even do this publicly. I never wanted.
Well, I remember when you and I first started talking, it was on the condition that you remained anonymous.
Exactly. I wanted to remain anonymous. I never wanted to go public. I was simply trying to help people who were trying to understand what was going on in the solar system. And I knew there was something wrong. I started researching it then. It has led me to the point that through observation, I started understanding what gravity really is. Now, my surprise is, as a lecturer, my students would ask me, what causes gravity? And I would say, we don't really know. We know this theory, and I used to teach them about universal theory that Newton came out with, and we can understand, we can understand orbits through it. I'll teach them whatever we could understand through it, but I don't know what causes it. And the students and I would start theorizing a little bit. What if it's electrical? Because it's...
I have a theory I'd like to run by you.
Yes.
So, because I'm still grappling with it, I've read your papers and digesting it. But when I stumbled upon the program I did last week called The Light Benders and dealing with matter and antimatter, and when I began to look at the atom and that we have an electron and then we would have a positron on the other side of antimatter. So the theory is at the atom level is that this is causing a spin. The atom is spinning, the electron is countering spinning, neutron, etc. As I was looking at that, Claudia, it suddenly impressed upon me, when you have atoms moving at these speeds, and whether they're a single atom or whether they begin to, group together, wouldn't that also be a foundation for gravity?
Okay, so let me explain first of all what happens. I figured out that matter comes out of light. Light is a photon. Now, a photon has no mass.
Correct.
It has no charge, and it moves at the speed of light. But it can be redshifted, because light coming from galaxies is redshifted. But Holton Arp said that this, he showed, he proved in his books. I have his book right here, Seeing Red. I just love this book.
Okay, all right, folks, hold that right there. This is too weird. Folks, we didn't plan this.
You have it too. Wonderful. I recommend this book to you a long time ago.
Yes, and I bought it, and this is my reference book.
Yes, that is absolutely phenomenal. He goes into such detail. He explains that redshift is intrinsic to matter. In other words, it's a property of matter like mass. It's not due to recessional velocity. He absolutely proves it here. And with that, he proves that the Big Bang Theory is false. He falsifies the Big Bang Theory with this book. So now we need to explain. He has a theory in this book about what causes the intrinsic redshift. He even shows that it's quantized. In other words, it changes in steps, and that matter, as it ages, the redshift decreases. So.
Okay, go. Okay. I have a question
now,
afterwards.
I had a little bit of help, and I had a little bit of help from James McKinney, because as I said, I read his book. I was fascinated because he was at a university many years ago when these observations were coming in. And he, like a good physicist who's really interested in the truth, took the observations at face value and decided, but this means that. It doesn't mean what they are saying it is. Okay, so he had the advantage of observing the data as it was coming in through NASA, which I didn't. So I read his book and I read about his observations and what he discovered. And one of the things he said, and he quoted Holton Arp as well, is that the redshift is actually caused by the fact that the photon is made up of two particles that are oppositely charged. And when it moves through an electric field, the two particles move apart. That uses a little bit of the energy of the photon, and that's why it gets redshifted. And then we do know that photons, gamma rays, split into two particles. They're supposed to be a particle-antiparticle. And then they're supposed to annihilate and become a gamma ray again. But he explained it in a different way. He says the photon is actually made up of these two particles. And when the electric field is not strong enough to keep them apart, then they go back into being a photon again, not annihilation. In other words, when I read that, I went a step further than he did, and I realized, wait a minute, the photon has two constituent particles in it. In other words, the particles were hidden in the photon. When it moved through the electric field pulls the two particles apart because they have opposite charge. The positive goes along the direction of the electric field, the negative one goes in the opposite direction. It splits them. It's because of the electric field, the electrostatic interaction, that the photon opens up into its constituent particles. But you see, I know that particles are actually fluctuations of space-time. And that's because I'm a particle physicist and I know about zero-point energy and about the fact that we have all these particles underneath the zero-point energy level. And they keep fluctuating, appearing.
Are those subatomic particles, like neutrinos?
Every kind of particle. Basically, they fluctuations of space-time itself. So in the photon, what we have is different particle possibilities. So depending on the energy, and when we have, say, a proton, antiproton, or an electron, anti-electron, because these two particles have the same mass, the separation interaction and the attraction interaction have the same strength. So, because gravity, you see, let's start with the electrostatic interaction. It causes two protons to repel, a proton and electron to attract. So a positive charge is attracted to a negative charge, right? Two positive charges move apart. The gravitational is the opposite. So two opposite charges in the gravitational, instead of attracting, they repel. and then two positive charges attract each other. So when you have the two particles come out that are a proton and antiproton, they have the same mass. The only difference between them is that they have opposite charge. So the interactions are the same. So you have the same force separating them as attracting them. So of course they go back to being a photon as soon as they can.
So let me ask you something. So the annihilation theory is that when you have a positive and a negative that interact, is that you have the annihilation, and that is where we get, they say, photons are produced and consequently gamma rays, which to the layman, to my mind, Claudia, that told me I don't need a star for light. If a photon can be produced by the annihilation of a positive and a negative coming together, matter, antimatter, it shows that there's a secondary source of light, isn't there then?
Yes, except for one thing. You see, all these theories they came up with, including antimatter, it blocks the innovation that will lead you in the right direction.
Mm-hmm.
Because what I observed through what James McCanney started saying, and I had already started thinking, is that positive and negative charges are separate in the universe. They are separate in the atom. The atom is positive in the interior. The nucleus is positive because of the protons. And then there are electrons on the outside. So protons on the inside, electrons on the outside. And every object in the universe is like that. So even the Earth's Van Allen belts, we have the inner one is positive, the outer one is negative. The sun and all objects, and he talks about that, he shows that even the Earth has a negative outer layer. So the proton and every object in the universe has the separation of charge in them. What causes the separation of charge? If the electrostatic interaction causes positive and negative to come together. If it was just the electric interaction, everything would be neutral. The atoms would collapse because the electron would be attracted to the nucleus. So there has to be an interaction to separate those charges. There has to be an interaction that causes the Earth and all objects to have a negative outer layer. So I started out by calling that the charge separation interaction.
You're actually almost talking about a cell. It's like if we have an outer covering, which is a negative, right?
Mm-hmm.
That's interesting. So what would be the inner core of that? Would be the positive?
The inside is always positive and it's denser. And then I started realizing that the two positives attract, and then I realized this is gravity. This is what gravity is. Gravity, what causes gravity?
Is it the boundary between the dense positive and that
there will be a boundary. There will be a neutral boundary between, because you have negative on the outside, positive on the inside. So in between, there will be a layer that will be somewhat neutral. Although we always have positive and negatives moving through all the layers, but the outer layer is mainly negative, is more negative, and the inside is more positive. Even in the nucleus, we have some negative charges in nuclei because we often have neutrons. And neutrons are made out of a proton and electron together. That's when the interaction collapses. And the electrostatic interaction is stronger. And then the proton and the electron comes together and forms a neutron.
Is there a magnetic field generated in that at the same time?
Yeah, well, the magnetic field is inbuilt into the fact that the particles have charge, and whenever charge,
so it's inherent to the structure itself. Okay, all right.
So whenever I'm talking about electrical, the magnetic is in there automatically because the electric leads to the magnetic.
Excellent.
But what we didn't have before is this interaction between gravity and the electric. It's the two together that causes all the structure we see in the universe. So it's the electrical that causes the photon to split, and then the two play against each other so that the atom is balanced, because it's the gravitational that forces the electron to move outwards. And then it's the electric that, after it's a certain distance away, the electric snags it and says, no, 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 don't move any further. So it goes into orbit around the nucleus, but it cannot get any further because it's the gravitational that keeps it from going into the nucleus.
So you said, and as I heard, that if there's not the attraction, then it's going to go back into a photon, right?
That's right.
That's interesting. So if we apply that to an opposite theory to the Big Bang, one of the things I'm reading in another book is that it says that science has yet to come up with the fact that sometimes some things just are. You know, you can't define them as a beginning. They just are.
Well, the thing is, we ask always, why are they?
Right.
How did they come about? How do they interact? We always ask. We're always seeking further understanding of the universe we're living in. That's what physicists do. We ask questions, and then we seek answers. Now, don't forget, what I basically said is there is no antimatter.
I heard it. I'm trying to figure that one out. That's okay.
Matter, there's only mass and opposite charge. Now, the photon splits into equal mass particles sometimes. That's when we see the particle, they call it the particle-antiparticle, because the two particles have the same mass and opposite charge. That's all. But the mass is just mass. It's positive mass. But, and then those ones, when it splits like that, they go back to being a photon as soon as possible. But when the photon splits into a proton and an electron, that's what they don't want you to know about, then they have different masses. And so the interactions are different. You have a stronger attraction between two protons than the repelling force between the proton and the electron. And that's what leads to the structure we see in the universe. And it's different because they have different masses. The proton is about 2,000 times more massive than the electron. And so they interact. You see two protons, we have two particles with a mass of about 2,000 times the mass of the electron. So the interaction is very strong. They attract each other very strongly. And that's what leads to the strong force in the nucleus and the gravitational attraction between bodies, because all bodies have at their center a very dense center, very dense in protons. And then that's what causes two bodies to attract each other. That's what gravity is. It's the long distance attraction between protons.
Yeah, I can see that, because it has to start down at the subatomic level and build up. I'm still trying to grasp, though, the aspect of, you know, if you have, for instance, in hydrogen, and I was reading one of the things at CERN that they were, and still are apparently, is trying to capture anti-hydrogen.
Yes, because what they that's big problem, because what they need now is an anti-proton and an anti-electron.
And they can't find the damn thing.
They can't, because the universe is built on protons and electrons. I guess it's possible for photons to split into antiprotons and anti-electrons. in other words, with the opposite charge.
Yeah.
But somehow, I don't know why, it doesn't seem to be happening. It seems that what we have is protons and electrons.
Yeah, yeah, yeah. And it's interesting. I mean, they're meeting it with failure after failure, but they're continuing to stay focused in on that. So I don't know.
I think actually, if it did happen, then if you had a proton and an antiproton together, these would go back to being photons, or may even interact with each other and form photons again. Wow. But there must be an asymmetry in the universe for us to see what we see. But what I find so fascinating about what I discovered is everything is the same. The structure of the atom and the structure of a star is the same. That's very compelling when I realize whatever you see on the microscopic is what you're going to see on the macroscopic. The laws are the same. Yeah. You see, Einstein spent the last few years of his life trying to unify electromagnetism and gravity. And here I come. I observe it. I start to understand, oh my goodness, I have just unified electromagnetism and gravity by realizing how it works and how I can now explain how all these objects form and why they are attracted to each other. I can actually explain. I haven't quantified it yet, I must say, because physicists like to eventually quantify so that we can come up with numbers. I haven't quantified it. I am still at the level where I can simply explain the universe the way it is through discovering that gravity is so much like the electrostatic interaction. It's so much like it. It's just a little bit the opposite, and then we have this asymmetry in it so that the interactions have different strengths.
Is that what Einstein was missing in his unified theory? That he was trying to basically connect everything to it?
Yeah, the thing is, he was using his general theory of relativity, where he described gravity as a distortion in space-time.
Has that been disproven, by the way?
Not necessarily disproven. I think he was right in that gravity is connected to space.
Okay.
Because the particles themselves, like I said, are fluctuations of space-time. In other words, particles are made out of what space is made out of, which is energy. It is energy associated with space. Space is not just empty. And these particles are like little dents in space-time where energy pops up. And that's what a photon is as well. The photon is a carrier of gravitational energy. And when an electron leaves the atom, an outside atom, valency electron, it absorbs a photon because it gains gravitational energy because the photon carries gravitational energy. So when it gains that energy, then the repelling force it feels for the protons increases. And then it's able to leave. It either moves to an outer orbital, or it actually gains enough energy to leave.
So that's the whole point when you said just a minute ago, there is no such thing as empty space.
No.
No, energy is constant, whatever form it may be in.
The universe is actually a substance. It's not empty. So
we know dark matter has been basically kind of thrown out now. And so it kind of leads physicists back to square one again. So what are we going to come up with, Claudia, is what is this, as you were just saying, it makes up the fabric of space, the very thing that we see, but we can't see. I contend man hasn't reached that point in knowledge that there will come a time when we will actually see a part of the spectrum that we will see this energy.
In a way, we see it. I mean, we know about it from quantum mechanics. We know that particles, even though they go down to the lowest temperature possible, will not lose all the energy. They will not stop ever vibrating because of this minimum energy that they have, which we call it the 0 point energy. Or
explain
the
that for people. Someone asked me, what is 0 point energy?
It's basically that minimum energy that a particle can go down to, and it cannot go any lower. It's inbuilt into quantum mechanics, because quantum mechanics has this little thing where particles have to jump through quantum steps, which is defined by Planck's constant. So energy levels can only, well, it actually comes down to measurement, where how fast the particle's moving with its position can only be measured down to a certain minimum value. And out of that comes the requirement that they must have a minimum energy. That's basically it.
Okay.
So there was something I wanted to mention, and that was, sorry, I've suddenly forgotten, but
that happens with me, and a lot of times, and it's going to do that because when and I'll just get the philosopher side of this. When I think of 0 point energy, that's where I think of God.
Yes, look, there is no way. Now, yes, this is what I wanted to mention, but let's talk about God first. There is no way that the universe is the way it is, and it was not created, because it is, first of all, beautiful. It is musical. It's the structure in it is perfect.
Yes.
But you see, physics has been divergent for a very long time. Physicists used to talk about unifying the forces in the universe. That used to be the main aim. Simplify things, unify things. But for years, it's been divergent. You get more and more fields that get more and more complex, that seem to get away from understanding more and more, because physicists don't even understand. Two different physicists working in the same field, say particle physics, but they work on slightly different problems. It's getting to the point where we cannot even talk to each other because they don't understand each other's work, because it's so complex. But it's not taking them closer to the truth. It's taking them away from the truth.
Yeah.
Because they've forgotten to simplify, they've forgotten to look at observation, and they've forgotten about the unification aim that we wanted, that Einstein wanted. It's becoming divergent. It's taking them away from the truth, from unification, from simplification. So through observing these stellar cores and how they are interacting, and trying to explain what these interactions are like and why they are behaving this way, I suddenly realized what gravity is. And I suddenly unified matter with light, gravity with electromagnetism. Can you imagine that? Of course, they're not going to listen.
No.
Because they don't want people to have this understanding. And mainstream physics will fight this to the death, because they've been divergent for too long. They don't want to know the truth. Even James McCanney was fired from his position because he started seeing that there were electric fields in space, and he started building electric fields into his explanations, his theories of what was going on, and his discoveries. He was fired.
That was heresy, isn't it? It's heresy to begin.
It was heresy.
Yeah.
So you can imagine, if I was still at a university and trying to publish this work, I can only imagine well, they basically fired me.
You know what they would do? And there used to be an old Pentecostal term we used. They'd give you the left foot of fellowship right out the door. And that's what they do, folks.
That's right.
You know, Claudia, I just absolutely so respect what you do for us here. I mean, the fact that you take the time to come here when you and I first talked about this show, and it's growing in popularity, and it's because what you just spoke for in the last 50 minutes in class in a dissertation is probably more math, more theory, in understanding structure of matter than most people here in probably the last decade. And I just say we're lucky. We're very, very fortunate to have you. I consider you as a friend, but to have you coming on here and teaching us, I just,
Well, it's a privilege for me, Wayne, because this is what I decided a long time ago. I decided that people were not being treated with enough respect. That I believe children are born geniuses, and the educational system takes it out of them. Bad teaching takes it out of them. The television takes it out of them. But people have abilities to understand. It's only that they need somebody to show them. Physics needs to be taken to the public, to the world. It's for everybody. Everybody who's interested in understanding the universe. To me, understanding the universe is understanding God. He created it for us.
Excellent, excellent, excellent analogy.
So it's for everybody. And you see, they've blocked, they on purpose made physics too complicated so that it could not be taken to the public.
Yep.
They did that on purpose so that people cannot understand the universe they're living in and the God who created it. They're blocking that.
And that's been part of my whole thing about, formal religion, is that they make God so complicated, so great, so unattainable. And when you talk about physics today, most people know of the word. I think, such shows like the Big Bang Theory is probably done more for the advancement of understanding physics itself and its many different disciplines. I've had to reprimand people here that tried to come saying some things about you. And I said, whoa, what? Back up, Cupcake, and just get down off your pony and let's just talk here. Do you know what Dr. Albers' degree is in? Don't be coming to me or to her and telling us that you know physics. Where's your PhD? Where did you study? Now, having said that, it doesn't mean that laymen like myself cannot come and learn from those who have been taught.
Mm-hmm.
And that's what you do. And it's a gift. I considered it a rare privilege. And the other thing is, folks, what a bargain. Do you know how much her class would have cost you? Yeah, we got almost nearly 300 people in here. And so I just appreciate you. And listen, so that people can have an opportunity, Claudia, please email me or email Claudia. You can go over to her YouTube channel. I've left the link.
Yeah, it's better if they email Scott or go through the Facebook Planet X News Facebook page, because to tell you the truth, I'm not very good at this email thing because I usually get stuck into writing. And Scott sometimes has to tell me, look at your emails.
All right. So we'll just do it for this one here. For the Physicist and Philosopher, email me your questions that you would like to have Dr. Albers address. and we will come in and we'll let her decide what she would like to present. And that way we can get it to where there's some interaction, Claudia. How's that? To where
Okay, yes.
Yeah, because
yes, I think it should go through you, Wayne.
okay. All right, that's what we'll do. And that way we'll make this more of a community show, because I kind of feel like I'm in the front of the classroom, and it's only because I'm closer to the teacher. And I want to make sure that, you know, the person stuck all the way in the back, not because you're hiding, but, you know, we want to make sure your voice is heard as well. Now, go ahead, Claudia.
So when I lectured, I kept asking my students, okay, do you have any questions? Do you have any questions? And I'd wait for them, because I know they're thinking, you know, how do I phrase my question?
Yeah. So, well, there's some smart people in here. I have to tell you, they're just like, I mean, I'm going, did I get in the wrong room?
Smart.
Yes.
Most people think they're not smart because they've heard other people say they're not smart. But when they start the thinking process, when they start realizing, oh, but I can understand that, then they realize they're not stupid at all. They can actually think. We all have a brain. We all have talents. Okay, not all of us can be good at the same things, but we all have an ability to think and understand.
Excellent. You see, folks, that's what is called intelligent discourse. We can have an opportunity. We may not all agree, but that's the great thing. You know, the fact that you could put forth the thought to even have the debate on, Claudia, that's what's important to me.
Mm-hmm.
Yeah. So I wanted to show you some things before we got out that kind of, I wanted to show you. Here we go. So we have been talking, as you know, that the planet is changing, right? Mm-hmm. So I wanted to run this by you while we have you as we close out. So this is apparently, folks, they're trying to make this like it's no big deal. But Claudia, I've been doing some research. Purple it's not, purple and white is, can you talk about this?
Well, this is not normal aurora. Aurora makes a circle around the poles. This is not normal. This is a plasma connection. This is what you would expect to have between the stellar core and the Earth's North Pole ionosphere. This is a plasma connection between one of these particles and the Earth.
I was thinking.
No other explanation than that. This is ionization of atmospheric molecules through a plasma connection between the two. It's an electrical discharge, basically, between the two. It's the only thing that can cause this.
I mean, lavender, folks. I mean, okay, now they'll tell you that, well, it's rare, but it happens. Yeah.
Well, the photons, the photons being given off, because what happens is particles. Usually, it's from the sun. We get particles coming in. They knock electrons off atoms. Then the electrons, some electrons then get captured again, and then they move down. They relax. They move down an energy level, and then certain photons are given off. So the purple one is the higher energy one. We can see some red and some green. The green is the mid-energy of the visible spectrum. The white is basically the green, the red, and the blue together. This is not normal, Wayne.
I don't think it is either.
This is more like normal aurora, because you see it's over the horizon. But a stripe like that, that's a plasma connection between two objects.
Yep, there we go. And that's why I pulled them up so people can see that there is a distinct difference. And so here is something I thought was real interesting, Claudia, that this is at a Science Daily. Existence of new form of electronic matter. This is amazing. I'm going to talk more about this in another program, but we're finding new substances that I think is coming out of the result of a lot of this quantum computing that they're actually discovering now. New materials. One time I want you and I to talk about graphene and that what it's doing to revolutionize. So here's one for us. Grand solar minimum could cause global cooling now.
Yes, except it's not causing global cooling. It's causing the opposite because it's drawing energy from the inside of the Earth. And the Earth is just as hot on the inside as the surface of the sun.
Well, a lot of people don't know that, and we're going to get into that at another time. I thought this was really interesting. So I guess the politicians are listening to us because they're hightailing it out, folks. They're getting their bunkers made. And so, Claudia, this is what they're saying as well, is because of all the changes that we are now in the middle of the sixth mass extinction.
It's been going on for quite a few years. I think, haven't we started hearing since 2011 about birds en masse falling out of the sky? What do you think is causing this? We haven't had birds en masse falling out of the sky for the last 1,000 years. Why is it suddenly happening? Because something has changed on Earth. And I believe we have these objects that are not only orbiting the sun, they are orbiting the Earth as well. It could be small ones. It could be just pieces of these objects that somehow, because these are huge objects, they are the size of stars. They are stars. Well, there are small ones in them, and there is a lot of debris associated with them. And there are a lot of planets in the solar system that also have gravitational energy and also have, therefore, an electrical potential difference across between the middle and the outer layer. And therefore, they'll be attractive to these objects that are looking for energy to absorb.
And that could be very bad for life on Earth, couldn't it? I mean, if it got too close.
This is why we are having biodiversity problems, because it has already been very bad.
See that? That is, I believe, the point that it's often how I look at things, Claudia, is that you can only begin to see the moment that the accident is happening. You're not aware of the forces that are coming together at that moment. And even during the accident itself, the inertia and the force is almost not perceptible until it stops. I think that's where we are. I think we're somewhere in between that connecting point.
And the weather changes are out of this world, Wayne. We are having almost continuous storms. This is not normal. I mean, I spoke to my brother and my mother today in Portugal. They are having weather they have never seen before. They're having tropical thunderstorms where it just pours with rain. And then they get a sort of flash flood kind of thing. And otherwise, it just rains continuously. It never stops. This is totally abnormal. Lisbon has never had this kind of weather before. They've never seen it before. Never. Continuous rain. It never stops. And it's either continuous rain or a huge thunderstorm suddenly. It just doesn't stop raining.
We are in the middle of something. I don't know, I tell people climate change is ever ongoing, but we're in the middle of something that It's not normal. You know, the great thing about getting older, you know, we're all eternal in our spirits, but is that you have a point of reference, Claudia, because I can look back to the 60s and I was a child that was outside all the time. And I can tell you, I grew up in California and grew up in Texas. And, you know, I don't remember the skies ever having colors in them. The only color I ever saw, and it was, you know, those rare times, was a rainbow.
Yeah.
I mean, that's the only color I saw in the sky. Today, go ahead.
Sorry, I did the same. As a child, I was outside. I used to love clouds.
Yeah.
I used to sometimes lie on my back on the grass and look at the clouds and imagine what they were. Like, oh, that one looks like a dog, or that one looks like a man in a boat, or, you know.
Yeah.
I used to love clouds, and clouds like that do not exist anymore.
No.
Do not see them anymore. They used to be fluffy, look like cotton wool, and be well defined, and they would be darker at the bottom, and they would come across the sky. All these balls of cotton wool would flow across the sky. They were so beautiful. That's what they were like. We don't have them anymore.
No, we don't. Because I remember my stepsister kicking my butt because we had an argument about the clouds one time. So, but it's changed. It's changed, and our atmosphere has changed. And that's what I appreciate about you, is that as these changes go forward, we can have someone who can help explain it to us, at least from the particle aspects of what matter is. And that's what I like.
Yeah, I mean, I started out wanting to be a physicist because I wanted to understand the universe.
Yeah.
And you know, here I am. I'm understanding it better than I ever did. This is like a gift from God to me, that I can understand gravity. I
think it's cool.
I am so happy that I can understand gravity. I never expected this, you know.
This is wonderful. And you've got the largest classroom, I think, of any professor I know of.
Yeah.
And it's growing. I mean, we're looking at this, and it's like as we're getting near the end of the program, and the chat room is filling up.
Yeah.
Well, all right. So our hour is up. It has been a phenomenal hour. You know, Claudia, it's what our hours teach me is, as Dr. Robert Lanza, who wrote Biocentrism, said, time cannot exist unless the observer is there observing the event. And what you and I, when we have these times, and look, we've got over 300 people in the chat room now, when we come together, time is distorted. Because to me, it becomes either condensed or it's just elongated to the point I don't recognize what an hour is.
That's true.
It is.
Because we're so interested in what we're talking about that our perception of time is not quite there, because we're so into the moment and into the understanding of it's interesting. So we're so interested that time just flows and we're not aware of it.
It is. We had to do a whole show on time. Wouldn't that be interesting to actually define the theory of time? Because I know from a philosopher's point, we think a lot about these things, and from a physicist's point, space-time is an equation that actually defines what our reality is.
Yeah, you know, what I didn't say is physicists like to quantify things, because in the end, you cannot compare two things without quantifying them. So if you want to compare two lengths, you have to say how long is the length of this and how long is the length of that. So this is where, you know, physical quantities, physics is a lot about physical quantities, and there's the most important ones are length, mass, and time. Those are the mechanics, physical quantities. And then we have to put some numbers to them, and then we have to say, we put a scale to them, and then we call that scale by a unit. For example, we measure lengths in inches or feet or meters. So we have to differentiate between whatever scale we want to apply, and then we have to use the same scale to compare two lengths. So we have to compare two lengths in inches, or we have to compare two lengths in feet. So that starts to come into physics, so that we can compare two things, and we can add two things, we can multiply two things, and
I got a feeling, folks, by the time we get into our 15th, 20th episode, we're going to have the whiteboard out, and we're going to be doing equations. Trust me.
Yes.
I already got the function that we can do the whiteboard. So, folks, you're going to have to bring your pen and paper with you. Oh, Claudia, thank you. It's been so much fun. You keep yourself. I know Scott's there and he's looking after you, and you have a place of sanctuary here. This is a place where you are loved, you are welcomed, and you are much cared for. So we appreciate you. And I appreciate everyone in the room tonight. Thank you all. Thank you for your respect. I thank you for your maturity, and you're definitely some of the best people out there. Thank you all. Be good to yourselves this week. I'll see you again during the week. Make sure, if you haven't subscribed, go over there to Claudia's channel, Planet X Physicist, subscribe and hit the notified button so that when she puts up her videos, you can actually begin to learn as I do. You see, I have the inside. I can actually email her and she'll email me back. So that's the only advantage I got in this situation. But it's taken years to earn the trust and the respect. So there you go. All right, folks. Much love to you. We will see you again real soon. All right. Bye-bye, folks. Everyone, welcome to Monday night and another